The first week of the course, the way the Strogats conceived it, is getting your ducks in a row. So the way you think about everything in this week is you have an infinite line, and on that line you can put ducks facing this way or that way. But once they face in this direction or that direction, the only thing they can go is they can go forward. And depending what's happening ahead of them, they can slow down or speed up. So basically only two things happen on a line, dynamics where state space is on a line. You cannot hop over the duck ahead of you. You cannot turn around, because to be able to turn around, your speed has to be zero. But once your speed is zero, nothing ever happens again. So the only thing you can do is you can either end up in some attractor. You might start on a repelling point, but if you're close to it, you just get pushed away, so you won't be there. And because it's an infinite line, you can run off to infinity, and that's it. So you wouldn't think it's worth a week of thinking, but it's very lovely because just doing this, you learn a bunch of stuff. And the main thing that you learn is the dangers of continuum. Continuum, we got used to it since Leibniz and Newton. The continuum is an amazing assumption. It says that no matter how small the distance is, there is a smaller one and a smaller one. And mathematics of continuum is very different than mathematics of discrete world. And quite honestly, we have no idea whether our world is continuous or discrete. It looks continuous, but for example, fluids looked continuous in the 19th century until a medical doctor and amateur scientist, Brown, discovered Brownian motion by looking closely at pollen in fluid. He realized that pollen is getting kicked around, so something is kicking it around. Eventually, they agreed that fluid is not continuum. It has molecules in it, and they jiggle and they kick around the pollen. And now mathematics of fluids, even today, is written as a continuum physics. And it turns out that that's not a bad idea, because when people today do numerical simulations of fluids, so they have 100 molecules, not Avogadro number of molecules, they already obey very accurately the continuum equations. And mathematically, assuming they're continuous, they're good, but there is a price to pay, and I'll come to it later in this. And you already realize this in one dimension. If the ducks can be infinitely small and move infinitely fast, which physicists ducks can do, things can go very weird. But first, to continue where we started, we found out that it's very easy to write one-dimensional differential equations, and it's kind of nice and easy to use them. So here is a popular thing, which is, something that the COVID era has given to us. We have a number of our compatriots who have learned the word exponential, which is a big step. A much smaller number understand what the exponential is. And as you sit in this classroom, you're part of an exponential. And that exponential is called population growth. It's not, how many beautiful Georgia Tech students are there, but how many viruses and how many bacteria there are. And in 19th century, where people obsess a lot about this kind of and that kind of human, and what's going to happen to industrial Britain. Malthus proposed a population model which is very scary. He said, if we have n people, so this is an integer, but it's such a large integer, millions and billions, that you can assume it's a continuous variable. And if they had the reproductive rate, R, like compound interest in a bank, per unit time, and we take time to be seconds or milliseconds or Professor Fenton femtoseconds, if the rate of change is proportional to how many people there are now, then things will go very bad. This is growth rate. Because you know how to solve equation like this. If its change is proportional to itself, its solutions are exponentials, or sums of exponentials called sines and cosines. So they either oscillate or they explode. In this case, if R is a real number and positive, they explode. So that obviously didn't make much sense. So a German biologist, population biologist, at this point, I don't know exactly what he did. Verhulst. He said, this can be right, because the planet would explode, we'll be all gone, so something is wrong about it. And what's wrong about this is that the growth depends on the amount of resources in the environment. And as the growth increases, the resources per person are decreasing. And at some point, we might run out of all the resources. So he said, this equation is okay as long as I say that the rate changes with the number of bacteria or humans. And he said, well, the simplest assumption is that the rate decreases as the number of humans increases, and the simplest thing to do is to do it linearly. So this parameter is now changing in this equation, and there is some critical value at which we reach overcrowding. So if we try to push over that value, the number of people will actually decrease. There will be less people than that. And he then wrote an equation, which is called Verhulst differential equation or logistic equation. Logistic means, when you have an army, you have to provide it with supplies. So this is your rule how to do your logistics. And if I write this line as 1 minus the number of people dividing by this critical value, and I stick this growth rate in here, then what will happen is when number of people is very small or number of bacteria, this will be negligible. So I will grow exponentially. Then there is some value where number of people is half the number of overcrowding value, where this function reaches its maximum. So I have the fastest possible growth. But then as n grows and approaches k, this starts getting very small. And when I exactly at this point, I will reach a fixed point, and it'll be an example of kind of equations we studied. So this is, a simple differential equation on a line. And people did experiments in population biology. They do experiments on bacteria and other populations. And what people found in the beginning, that Verhulst was very good when you looked at yeast, bacteria, there are kinds of things it was very good for. But then there are some things which are more or less important to us, including fishes in a lake and humans and moths. So there are population which have some external cyclicity, like annual growth rate and decay imposed upon them. And they do very strange stuff. And that'll be actually the second part of this course. What happens is they seem to oscillate wildly. So if you go to the same forest and climate is not changing very much, from year to year in the same habitat, you might find few moths, very many moths. And if you do it for a long period, which you can maybe not do for the moths in forests, but other populations which are, driven cyclically, not just in continuous time, they do strange stuff. And today we call it chaos, but at that time they didn't know what it was or how to describe it. But basically, this equation was just, as you can see, a parabola. Has attractive zero here, has a repelling equilibrium. If there is not a person, if we had a zero, nothing will happen. But like Yahoos in Gulliver's Travel of Swift, if there are few of them, suddenly there'll be many more of them. And that's what we did in first lecture. You found there was a flow going from repelling to unstable. And thinking of negative people doesn't make sense. So this is avoided. Negative numbers of people, of course, we plug these negative people, but the ones that are virtual don't exist. We don't have to do it. So that's where Verhulst and the usual tricks work, If you start here, you speed up, you slow down. So if you draw a face portrait, you will see that, they have some symmetries and they're cute and they're being described well by Strogatz. So we can do this for a while, but now comes something that's very important, and I'll actually use my own professional diagram of what I actually do for a living these days. And that is called linearization. So in this course, and more advanced versions of it, we teach you nonlinear dynamics. That's a science of non-elephants. If elephants are linear, rest of biology, which is almost everything, is nonlinear. So you feel I can forget linear stuff. That's for babies. Actually not. It turns out that to understand things like general relativity and many, many other things, understanding linear physics is very crucial. And that's illustrated by my little problem here. This is called field theory. So you can imagine you have a piece of land and there are blades up, and that's why Germans gave it that name, Feldtheorie. It looks like a field with blades of grass. They have different height, and many theories of both fundamental of nature, but also population theories that approximate or assume that there are continuous, like electromagnetism, an example of it, continuous field over space-time you're interested in. And now suppose this is Tennessee, and in Tennessee, the earth is flat. Now, those people are not dummies. They work on assumption that earth is flat, and it's done wonders for them. And indeed, locally, earth is flat. And a very powerful way of understanding how more larger so-called manifolds, things that have many folds in them, how they function is to tile them with little flat tiles, which are all flat. But when there are lots of them, you can tile them, and that's called algebraic geometry, or geometry that starts with Poincaré, understanding qualitative features of it. And linear is extremely important part of it. So when somebody teaches you an equation, Maxwell, Navier-Stokes, Einstein, whatever equation, they write it in a flat earth approach, which is to say that locally they just vary everything by little amounts. And that's what the equation is locally. Now, globally, it's something else. So at this point, we don't know anything about quantum field theory, but we have these little problems like this one that I showed you last time. What happens if my ducks are following some law where they speed up distance pi from the origin, then they pile up a distance pi over 2 pi, and so on. So this equation here. Can we say something, not only where they end up, but how fast they do it? Can I get more information? And that's what linearization does, linear stability. So the very abstract idea of linear stability is that I have my law. Right now it's in one dimension, but next week it will all be in two, and a month it will be in three or more. And my law says that if I start here at x times 0, and now x can be 200-dimensional vector, or could be on a line, could be 1, 2, 3, any number of components. Remember, x is x1, x2, array of numbers to the dimension of your particular state space. And this thing now says, and that we'll discuss next week, I can go in my little step following my law, differential equation, that's called integrating the equation, and end up someplace at time t. And in deterministic systems that we are only studying this semester, if you have fully specified, arbitrarily precisely specified state of the system at time 0, like all the temperature, pressures, wind velocity, etc., then in idealization, that's deterministic mechanics, at any time later, there'll be one single possible outcome. You'll be only in that particular state. So that's good. But then somebody says, well, actually, you didn't start there, you started here. And there was a little vector, a little perturbation called eta, just so we can do some Greek letters. And what will happen to a neighbor who started there? How does that work? Well, you say, no big deal. I'll just use my program and I'll integrate this one. And I'll find out that it does whatever it does. So what happens is that, this is x0 plus little vector is this initial condition. And now what this thing here is, where you ended up, the distance has changed. So there is some new vector eta at time t, and you ended up at a point which is x going time t, having started at x0 plus eta 0. This is where you end up. So in principle, when you know your trajectory and you have the law, you can compute all the trajectories. But then you say, you know, this is a little bit stupid because if this neighbor is very close to me, why am I repeating all the work I've already done just to find out that somebody who is 3 angstroms away from me, you know, 1 minute later is 4 angstroms away from me? Why am I recomputing everything? And that's now the idea of linearization. You can say, I can actually approximate my neighborhood by a flat Earth hypothesis and find the consequence of it sometime till later. And it turns out to be a powerful idea. So it's easiest to illustrate it by a fixed point. Suppose we have a fixed point and we have our law that says start at fixed point and continue, and you know, I can decorate it with time, etc. But basic thing is start at fixed point, and law says compute the velocity at the fixed point. But that's clearly 0 because fixed point doesn't move. So my velocity stays 0. And that you usually use in practice, you use that condition to find fixed points. You know your velocity field, but you find the ones that work. And now you say, I'm at my point x0 in the space where nothing happens. So that's my point. But if you start a little bit away from that point, eta, usually the velocity is 0 only at the point, you know, that you have already seen on one-dimensional line. There are very good reasons why you don't want to have intervals in which nothing happens. That makes it very hard to use smooth function and this and many powerful things. So usually just a local thing. And what will happen is this guy will not move, and the tip of this little neighborhood vector will change in time. So we can find the equation for that. You know, eta at time t is where I find myself at time t, right? Minus the fixed point. Sorry. But, you know, I have my law that says that the velocity of eta, well, which is now same as the velocity here, because if I take time derivative of the two sides, this is constant, goes out, xt I can say, well, that's almost like velocity at the fixed point. but I'm not quite there, so I'm eta away. And by almost like that, it means that I can do a Taylor expansion. So I can write this as f defined at the point. Sorry, I'm making x into a star plus the first derivative with respect to variable x. This is not with respect to time. It's called velocity gradient, how velocity changes as you change the position. Evaluate it as you do in Taylor series at the point you're expanding around. Times this. We're in one dimension, so I don't have to take care of the indices, times eta. Plus order of eta square. So if eta is small compared to the scales I care about, the distances I care about, I can neglect everybody there. And now I have an equation for eta itself, which says that, because this cancels that by fixed point condition, I have an equation that says that eta dot is proportional to eta times a number, because this is a number evaluated only once at the origin. And this equation we know how to solve. We just did it for Malthus equation. If some distance is its change is proportional to distance itself times a rate of change, then solution will be exponential. So that means that as I look in time around my fixed point, my neighborhood will just be flowing away if this is a positive number, or falling exponentially toward me if this is a negative number. This is a variation in space, not in time, of my law as I look at neighboring function. So now we have much more than just the picture that we used to have. I run away from here, I fall in there. Now I have the rate of change, because now I know that if this derivative this gradient is larger than 0, I'm stable. And if this is negative, I'm unstable. Thank you. So now, tricks of trade. Teachers make errors. Sometimes they do it on purpose, but sometimes they just make errors. So now we know that if I look at 1 over this quantity, f, remember f was velocity. When I took its change with respect to distance, I got rid of units of distance. So this thing has natural interpretation, and when you look at it as exponential, you understand that's the width of exponential. This is a characteristic time. For time shorter than that, you can say this is my neighbor. For time larger than that, you say, I don't know this person. This is too far away from me. And this is a very crude way of defining your neighborhood, but quite useful and powerful. So that's linear stability. Right now it looks totally trivial because we're looking at fixed point in one dimension, but it already gives us a little bit of information. So if we go back to problems that we used to have, like this row of ducks that are being, pushed back and forth depending where they sit on, like by a wave in the sea. Now we know the following thing. If we go and look in this neighborhood, around 1, for example, we find out that the velocity gradient with respect to this point, fixed point, which is pi, is derivative of sine function evaluate phi. Derivative of sine is a cosine. Evaluate pi, it's 1, right? -1. So this is -1. So this is attractive, and its characteristic time is, roughly speaking, 1, because 1 over this is attractive. Now, if I look at this point, stability of 2 pi, this obviously has a positive slope, +1. So now I know not only that I have things that are stable or unstable, but I know literally in terms of a number that'll turn out not to depend on choice of coordinates. When you get very fancy and you do general relativity rather than little oscillating sines and cosines, this will still be a number which characterizes how long do I hang around this neighborhood, and that can be very important. There can be very small neighborhood, big neighborhoods, and they are described by the flat Earth hypothesis. So that's useful thing to know. Now comes the stuff that the ducks cannot do or computers cannot do, but this mathematics of continuum does, and you have to be very careful of it, because at this point it's kind of simple and obvious, but when you start solving difficult problems in theoretical physics, like trying to understand the nature of turbulence or something like that, then it might be not at all obvious what's going on. So one thing that can happen is that I can have stability at a fixed point, which is not a number, because, I told you there are stable guys, unstable guys. But what happens on the border? Now, the border is the hardest place, because on the border, you don't know whether you're going this way or that way. So what happens when the first derivative, first variation with respect to space of your velocity field is 0? And, weird things happen, and it's actually important very often to understand this. So here is a possibility. If I take a function, I take my velocity to be x cubed. Remember, we're only on one-dimensional line. This is x. And in vertical, we are plotting the velocity. So now what happens is if I take one derivative, I get x squared, which means that the function is totally flat here. And then after a while, when the second term kicks in, the second derivative, it curves up. And because I started with x cubed, it looks something like that. Maybe it grows positive on this side, goes negative. The slope goes to 0. And that means that if I'm here, I will flow away. And if I'm here, I'll flow away because I'll get more and more negative, more and more positive. So this is an unstable fixed point. But I don't know this from my original criterion because x is exactly 0. So I'm on a border, I don't know, in linearization where I'm okay. So I have to do some nonlinear analysis to see what will happen. In this case is pretty obvious. Now suppose that my velocity field look instead of this like x squared. And obviously, if I flip this to be minus sign, I would make this into an attractor. But so now what happens is my velocity looks like a parabola. So on this part, it's positive. So if I was here, I'll get bigger and bigger with positive increments. I'll be flowing this way. On this part, I get further and further away, so I'm still flowing this way. So now this is a weird situation where half of this is what we used to draw as a black dot. So on the left-hand side, it's an attractor. On the right-hand side, it's a repeller. And then, even worse thing can happen. Suppose that all derivatives, not just the first one, is, a very, what we call degenerate. It has some connotations, but case is that, if all the derivatives were 0, or, many of them, not just first and second, then I would find out that on this line, there are whole families of points that don't seem to move anyplace. So there can be whole degenerate, families, and I have to go to some high derivatives, do some tricky stuff to understand what's really going on. And this is a subject of mathematics that started in the 19th century. That's a very important subject, which is called analysis. So that's what some of our colleagues in math department do. But this is still relatively innocent. Now, if you're not careful, things can go weird. This just says my linear analysis, which nobody said should have been perfect, doesn't work. But, I can fix it by working a little bit harder. But then there is something that in physics we kind of avoid, but mathematicians have to worry about a lot. That if you think about these differential equations, it's not at all obvious that this assumption of determinism is correct. You know, I told you I start at some point. I use my little grinder called integration program, and I end up at unique point time later. And that is fine until we let this continuum go very nasty on us, and it does it in two ways. You know, one of them right now you're not so careful about because this attracting fixed point, well, you know, there were infinitely many ducks at the same spot eventually, but okay. But what happens is if there is a repelling point which repels you infinitely fast. So what happens when you have infinities rather than, you know, nice bounded velocities? So here is a very simple example. Again, we just plot our function, velocity function. And the simple example says, take a velocity function, which you can easily construct yourself, which has infinite slope, just at this point, and it's, you know, nice anyplace else. So it doesn't have infinite velocity, but it has infinite change in velocity. So this is f of x. It's repelling, but it has a property. It's not repelling 6 feet per minute, but it's infinite. F of 0 is the fixed point, obviously, is infinity. Now, what you can do in that case is say, but you know, let me kind of understand it in a neighborhood and maybe I understand it how it works. So what you can do in a case like that would be the derivative, right? This particular function, for example, you know, could be that velocity, which is this f of x, is cube root. You know, so whenever you raise x on power less than 1, you know, it shrinks here and grows as x grows. Above value 1, but below 1 it misbehaves. And now you can integrate this because you can say, well, dx dt equals x. So forget that there's some problem. You just say that's what it is. That means I can write dx over x 1/3 equals dt. Now, that's just ordinary integration. You know how to do that. You integrate both sides. And this is just t. And on the left-hand side, there is 3/2. And you increment this by 1 by integrating, so x to the 2/3. And this is good up to constant, right? So now we have a problem because if I wasn't so smart, I didn't know how to integrate, I noticed that x of t equals 0 is a solution. So if at all times I just sit there, that's a good solution. But now I've integrated it, so I find out that actually, as the time goes, x moves as this function, you know. So there is also a solution. And if you screw around with this a little bit more, you know, this violates our starting assumption. We said, well, there's only one solution for every initial condition. Now there are two, and it turns out there are actually infinity of solutions. And what has happened is that this particular neighborhood is so singular, you know, the ducts are so compressed that when you try to probe it, everything explodes. And there's a, you know, infinitely rays that can come out of this particular initial condition. Now you can say, you know, this is just some nonsense, because what do we care? I can deal with that. You know, I just stay away from this neighborhood, no problem. Okay. So this is a situation where, you know, everything looks under control, except there is some little singularity. So maybe you can deal with it by putting some physical intuition in what you need out of this particular problem. But then come this totally innocuous looking equations that actually lead to real explosions. So this will be imitation. So here's a totally innocuous equation. Say, well, you know, velocity is 1, but that's boring. Now, we have already done these linear examples. When we add x, we know that solutions will be exponential. So what's the next thing I can do? I can add x squared. So, well, it used to be in linear case that, you know, I was going faster and faster proportional to how big I was. Now I'm going much faster because I'm proportional to the square of how big I am. And, but it's an innocent equation, you know, I can leave it to you to check it, but it's almost obvious that xt tangent of t is a solution. Now, what's wrong with this solution? You know, if I plot it, I get that tangent first grows linearly, that's fine, because, you know, this was constant, so I would have a linear growing position. But then it speeds up, and by the time I get to the pi, it goes off to infinity. So I have a blow-up, you know, innocent equation, but its solution just grows so uncontrollably that once I've reached pi, I don't know what's going to happen after that. Again, you can say, well, all right, you know, something happens, but it's just one-dimension problem. I know how to do this. But then it turns out that if you think very hard about this problem, which many of my colleagues really do think very hard. And why do they think very hard about it? I mean, there is a vulgar reason which is called $1 million, which at the start of our millennium was real money, but now it's not money anymore. But this is a millennium problem for Navier-Stokes equation. So Navier-Stokes equation is a little bit like this, except on the left-hand side, you're looking not at one as value x, but you're looking at three of them. It's the local velocity of the fluid. And on the right-hand side, it has some derivatives and stuff. It's called partial differential equation. It's so innocent that one can derive it in about 2 weeks of teaching continuum physics course. And to this day, it's called Navier-Stokes. The little ducts are called infinitesimal volumes of fluid. And they have a property that, they follow the rules and they also rub against ducts next to them. That's called viscosity. And you could imagine, but nobody has demonstrated it, and because you're in 3 dimensions, that you could give orders to the bunch of ducts in such a way that they would get together and suddenly produce infinite velocities. Now, intuitively, it doesn't seem right because when we look at boiling things, we don't see, temperature like in sun or something that would happen if you had this amazing velocities. But this is a question of continuum mathematics. We have formulated Navier-Stokes equations as equations that assume that fluid is continuous. And we do not know whether they have solutions like that or not. So by the time you get into more dimensions than one, this gets to be serious. Going back to, simple things, innocent things, there is one thing that happens often in our world, but cannot happen in one-dimensional world. And that is that our intuition about our world comes often from hook, which is, I push on something and that thing will push back. I push on, a pendulum, it'll come back. I push on a metallic blade, I hit it and it'll come back. And if there is not much of a loss to the air is not a very, thick fluid, that thing will oscillate for a while. And if I put it in a bell jar, it'll oscillate a very long time. And if I take a perfect silicone sphere and I'm trying to see whether I can measure gravitational wave, this thing will oscillate 10 to the 13 times until its oscillation goes to the half. So oscillations are very important in our life, but they just cannot happen in one dimension. And, it's pretty obvious why. Here is our one-dimensional world. Here is our phase part, its velocity. And no matter what you give me, so you give me some velocity profile like this, for which I know that I have attractive point here, repelling point here by our rules. The actually ducts are aligned on a line, and if they try to go back of necessity, they will have to decrease their velocity to 0 so they could increase it to be, decrease it for it to be -0. But the moment they do it, they're frozen. So, they're here, for example. So there is no way of reversing anything. And for that reason, one-dimensional world is totally devoid of oscillations. And this turns out to be important to us already, in many experiments that especially our biophysicists do. When you have very small objects in fluids start feeling extremely viscous, more and more like honey or tar or something. And in that case, in our equations, you can neglect the acceleration terms in various equations, and you get exactly these lower dimensional equations where you only care about friction, and friction is always just proportional to velocity. So there are many important problems having to do with swimming of microorganisms and robotics in sands and many other things that our people deal with on the campus of Georgia Tech and every place else, in which this is not a stupid observation. The no oscillations is very important. This brings us to kind of things you are very familiar from physics, which is, often it's possible, and sometimes it's absolutely essential, that when I write my velocity field, so this F is velocity, it can be written as a derivative of a potential. Now you have to be a little bit careful, because what you usually learn about potentials in mechanics, in Newtonian perfect mechanics, there the derivative of this potential is actually the force, the acceleration. But in these very viscous situations that we just looked at, you can call, if there is such a function, you can call it a potential. And it's a very useful thing to think about. It's about the viscous things, or friction dominating. But drawing this function whose derivative you look at, it can be quite helpful. So suppose it's a function that is, let's say, cubic. So first example. Then when you look at its derivatives, you care about the extrema. So you will find out that this function, if it has, top and bottom, they will correspond to equilibria or fixed points. And the sign is designed in such a way is if you are the bottom of a potential. So, so there's some kind of wall here. So you cannot, only thing you can do is you can roll down this thing. You cannot penetrate it. Then you'll slide down to the bottom and you'll stop there because friction will prevent you from doing anything else. But if you start at the top, on one side you'll slide down, on the other side you will go far, far away. So the main rule about the potentials of this kind is that if I look at the change of potential in time, the only dependence is on where I am, because potential is just function that depends on where I am, but where I am depends on time. This becomes by chain rule, this becomes this derivative delta x times x dot. But by our definition, this is minus x dot. So this is a minus dv dx squared. So potential always works in such a way that it's always decreasing, because this is a positive number, this is minus sign here, so it's always decreasing. It's all downhill always. So sometimes having a formulation in terms of potential is very useful, especially in higher dimensions, but you can only see it here. The way you think about your particular problem then is you have a landscape which has some valleys and some mountain tops, etc. And every time you have a flat bit, either at the bottom or at the top, that gives you an equilibrium. And then as you look in the linear neighborhood, flat Earth world, if it's a hole in all direction, you ended up in a hole, or you ended up on a tip, or you have various possibilities with ridges and dales. But this intuition is very helpful, and goes all the way to neuroscience, where people try to figure out how do you remember, how does your brain remember anything? So one hypothesis is that that's called a Hopfield model, which is not correct, but but it's very inspirational for the field. Is to say that you got lots of neurons. Every neuron is one of these coordinates, so in some very high dimensional space. But there is a potential function which says, you excite me in some way, which means you present me with some image or something, which means you put me someplace in the state space of the brain. And then this thing sluggishly drags you down until it finds a hole and says, aha, this is letter A or something. So this is, the beginning of computational neuroscience. Now it gets much fancier today, but that's one of the cases you run into this. Another case that one tends to see very often is that problems that we deal with tend to have symmetries. So it often happens that, I'm here, or my experimental setup has some particle or some state, and there is no obvious reason why one should prefer left to the right. And you can check that if your equations don't change, if you change left to the right in your coordinates, you say, I have a symmetry. In that case, potential cannot look like that, because this is very asymmetric. On the left-hand side, I'm going downhill. On the right-hand side, there's some mountain or some ridge, totally different. So you end up looking, and this happens all of the time, including, the paper I'm writing this month. You start looking at potentials that, have a valley, but you don't know whether it's a left or right valley. That's important. That's called double well. But if you change x into minus x, if you flip this picture, this will just go there. And you can decide to scale this thing in such a way that exactly at x minus 1, you have a bottom of the valley. Now, the moment I draw this for you, you can guess what the simplest polynomial would be. If I only allow quadratic terms, it's parabolas. It can be parabola. If I add a cubic term, left and right will be different. So it can be that. So it must be some quartic thing. And you can write it down. When x is very small, it looks like inverted parabola. When x is very big, it doesn't matter what happens here. It's just growing very high. And it has to be symmetric, so it has to be fourth order. So I can decide to write this potential. I have lots of freedom in how I choose the scales, coefficients, etc. But units of time, so I can bring it in some nice form. So that's a quartic potential. And you can, it has common factors. So you can obviously write as 1/2 minus x square 1 minus x squared minus x. And you can check that it's one extremum is here, but the two other flat parts at plus and minus 1. And there's a minus sign in front. And this actually turns out to be very important in lots of things, from fluid dynamics to chemistry to quantum mechanics to making computers and bits, etc. The system is bistable, meaning that you either end up stably here or stably there. But then in the real world, you have various external things you can apply to it. So you can kick it, you can heat it, you can force it, etc. And you can choose whether you are in a plus or minus 1 state. And lots of things can be described by that. So this is about the end of useful stuff we can learn in 1 dimension. Thank you for following me on Twitter, but okay.
It's always entertaining.
I wish, but